So today in class you guys had worked on solving exponential equations. We did that by equating exponents. We did that by taking a logarithm of each side. Well, now we're going to work on solving logarithmic equations using similar techniques to what we've already done. So just like when we talked about exponential equations and we said when two bases are the same, their exponents are equal to each other, we can apply the same thing with logarithms. And we've already talked about this in class, so this shouldn't be new, but you should write it down anyways. For positive numbers, b, x, and y, where b does not equal 1, log base b of x equals log base b of y, if and only if, so that's IFF, stands for if and only if, x equals y. So basically we know that if we have the same base, our arguments, or these numbers right here, have to be equal to one another. So looking at this first equation, we have log base 3 of 5x minus 1 equals log base 3 of x plus 7. Well, notice that they have the same bases, which means that these numbers have to be equal to each other. So 5x minus 1 has to equal x plus 7. Let's solve by putting all of our x's on the same side. I'm going to do that by subtracting x. 4x minus 1 equals 7. I'm going to add 1. 4x equals 8. Divide by 4. X equals 2. And again, it's always good to check your solution. So I'm going to plug in log base 3 of 5 times 2 is 10 minus 1 is 9 should equal log base 3 of 2x, 2 plus 7, which is 9. So log base 3 of 9 equals log base 3 of 9. That's true. We also know that this is the same thing as log base 3 of 3 squared. So we're going to get 2 equals 2. But we really don't need to go any farther than this because this shows equality right here. When it's not convenient to write both sides of an equation as logarithmic expressions with the same base, so like in the last problem we had log base 3 on both sides, when that's not convenient, you can also exponentiate each side of the equation. So for b is greater than 0 and b not being equal to 1, we know that if x equals y, then b to the x equals b to the y. Remember, the bases have to stay the same, and you'll see what I mean with this in an example, but sometimes you can't do the logarithms, so we can change it to exponential form. We're going to exponentiate each side of the equation. So in this question, we're asked to solve log base 5 of 3x plus 1 equals 2. Well, I can't possibly make this 2 have this logarithm of base 5. I can't just make it appear out of nowhere. So instead, I can take it, remember we said if x equals y, then b to the x equals b to the y. Well, here, x equals y, so b to the x, so b to the log base 5 of 3x plus 1 is going to equal b to the 2. Now, you won't write the b. You need to figure out what base you want, but I wrote this just to help show you that this is what your exponent's going to be and this is what your exponent's going to be, x, y, and it's going to be b to some power. Now, how do we decide what b we want? Well, I want to simplify this as much as possible. So if you remember that property, we said that if our base here and our base in the logarithm match, it's kind of like it's equivalent to 1, and then it's going to equal this number. So if we have base of 5, 5 to the log base 5 of 3x plus 1 is going to equal 5 to the second. These are going to cancel out in a way, this base of 5 here and this base of 5 here, and we're going to be left with 3x plus 1 equals 5 squared, which is 25. So I'm going to subtract 1, and I'm going to be given 3x equals 25 minus 1, which is 24. I'm going to divide by 3, and I'm going to see that x equals 8. Now I want to check my solution, so I'm going to stick this value of x back in. We're going to have log base 5 of 3 times 8. That's 24 plus 1 is 25. And hopefully that's going to equal 2. Whoops. Sorry. We're going to see, does that equal 2? Well, log base 5 of 5, log base 5, of 25, is the same thing as log base 5 of 5 squared. These cancel, these make 1, they don't cancel out. We're left with 2 equals 2, so we know we did it right. Now here's the most important part about logarithmic functions and solving for them. Because the domain of a logarithmic function generally does not include all real numbers, so what I mean by that is we have these in our graph. Before we were graphing exponential, and they kind of look like this, or they look like that. Well, sorry, let me erase that. The domain for those was all real numbers. But now we're working in logarithmics, which we have a vertical asymptote. So our graphs are going to look like that, or they might go like that. But our domain is going to be limited based off of where the vertical asymptote is. So because the domain of a logarithmic function generally does not include all real numbers, you should be sure, whoops, oh, sorry about that. You should be sure to check for extraneous solutions. So what this is just saying is that even though I've been trying to get you to check your solutions already, because of that vertical asymptote and because the domain is not all real numbers, there could be extraneous solutions, and you have to check for them. So looking at an example, we're asked to solve log of 5x plus log of x minus 1 equals 2. Well, because they have the same base, no base is written, so 10 is implied. We can use our properties of logarithms and condense this. So since it's adding, in reality, that's actually 5x times x minus 1. And that's going to equal 2. Well, if we simplify that, we have log of 5x squared minus 5x equals 2. Because we don't have logs on both sides, we can't try and set two logs equal to each other. We're going to exponentiate by taking it to a power, making it an exponential function. We want to use base 10 because that's the base of the log. So 10 to the log of 5x squared minus 5x is going to equal 10 squared. Because these bases are the same, we're going to get 5x squared minus 5x equals 10 squared, which is 100. Put this together, I can first of all divide by 5 and get x squared minus x equals 20. Looking at that, we want it all to be on one side so that we can factor. So x squared minus x minus 20 equals 0. To factor this, we have x minus 5 times x plus 4, because it multiplies to negative 20 but adds to negative 1. That equals 0. So x minus 5 equals 0, and x plus 4 equals 0. So x equals 5, and x equals negative 4. Now we have to check our solutions. So going back to our original equation, which was log 5x plus log of x minus 1 equals 2, We have for x equals 5, log of 5 times 5 is 25, plus log of 5 minus 1 is 4 equals 2. Well, this is the same thing as log of 25 times 4, which is 100, equals 2. Log base 10 of 100 is log base 10 of 10 squared equals 2, so 2 equals 2. So this solution of 5 works. Looking at negative 4, we're going to have log of 5 times negative 4 is negative 20. Plus log of negative 4 minus 1 is log of negative 5 equals 2. We've always said that the numbers that we're taking the log of have to be positive. Neither of these are positive, so this doesn't really work. This is an extraneous solution, so our answer is going to be x equals 5, and that's it. So we'll get more practice with solving these. It just takes remembering the properties, remembering how to get the right bases, what to cancel out. It's just about manipulating to help you. So tomorrow in class, we'll practice problems to get more comfortable with this.